Good evening, everyone, and welcome to RASC Toronto Centre Online. I'm Dr. Elena Hyde, the second Vice President of RASC Toronto Centre, and this is our March 2021 Speakers Night. So welcome and hope you're all having a good Wednesday. This is one of the two types of gatherings that we have online these days, not at the Ontario Science Centre due to the pandemic. And our President Tom Luton will be talking about those various programs later on this evening. But first, we have a very special tonight sort of event to kick off. For our speakers night tonight, we are delighted to welcome Dr. Nienke van de Marel from the University of Victoria to tell us about planets under construction, in particular exoplanets or planets outside of our solar system. It's always fun to think about life around other stars and other kinds of planets out there in the galaxy. But before we get too far away from Earth, let me go ahead and introduce our fantastic speaker. Dr. Nienke van de Marel is a Banting postdoctoral fellow at the University of Victoria since about 2019, working on planet formation using the revolutionary ALMA telescope. So before this, she was actually for 2 years at NRC as a postdoctoral fellow at the Hertzberg Institute for Astronomy, and of course 2 years as a parent fellow at the University of Hawaii. So she's been a lot of amazing places. She got her PhD cum laude in 2015 at Leiden University in the Netherlands, where she originates. So Nienke is also the founder and the host of Nerd Night Victoria, just in case you want to find her after this sometime. They do public science talks and informal every third Wednesday of the month, I believe, since about August 2018. She is also a future assistant professor back at Leiden University in the Netherlands in about, September, I hear. And I, for one, really look forward to having an inside connection for Leidsekas. So we're very lucky to have her with us here tonight, and is a huge fan of fictional and real planets outside of our solar system. I know that I personally am very excited for this talk. So without any further ado, Dr. van der Merel, please, if you could make it so.
Yes, I am sharing my screen. Hello, welcome everyone. Thank you for coming to my talk. So today I will tell you about planet formation and exoplanets. And one of the first questions that I often get whenever I tell people that I work on planets is, are there aliens? Are we alone? Or is there life out there? Well, my first response to that is, I'm really sorry, I'm not allowed to tell you because I work for the government. Get it? I did not. Okay, I will start it again. Okay. Hold on. Ah. I am sorry about that. Am I back? Okay.
As you know, sometimes technical difficulties can happen through all kinds of different reasons and effects, but we appear to have the wonderful Dr. Van der Marel back with us with her screen share. So we're going to try this one more time. As I say, the best talks are always worth waiting for. So Dr. Van der Marel, please take it away once again.
Yes, thank you. So indeed, I'm going to start again. I'm going to tell you today about planet formation. And so one of the first questions that I often get whenever I tell people about my job is, are there aliens out there? Are we alone? And my response to that is, well, I'm not really allowed to tell you that because I work for the government. Yeah, and then I start laughing because obviously this is a joke. I know you can't see my face that well, but this is a joke. We don't know if there are aliens out there, but it's a very, very exciting thought that there is life on other planets. And it's not even that unlikely if you think about it, because there are so many exoplanets out there that we already know of. So exoplanets are planets around other stars than our sun, so elsewhere in the universe. And the development of this field has been very, very rapid because, back in my day, around the time I was born in the late 80s, we only knew 9 planets, the planets in our solar system. Then in 1995, the first exoplanet around another sun was discovered. And since then, we've seen increasing and increasing numbers every single year. And right now, the counter is more than 4,000 exoplanets, which means that planets are actually very common around other stars. And I may want to point out that we lost Pluto along the way. It's no longer called a planet, it's now called a dwarf planet. But since we have so many other planets elsewhere, maybe that doesn't really matter. We have so many planets where we can look for life, where we can expect aliens. So how do we find exoplanets? And this is already the first tricky bit, because trying to see a planet orbiting another star is like trying to locate a tiny little firefly right next to a lighthouse. You're looking for something very, very small, very faint, right next to something that is super bright. So how do you do that? Well, one of the most common ways, which is an indirect detection method, is called the transit method. In this case, you basically monitor the brightness of the star. So you measure the brightness of the star again and again and again as a function of time. And whenever a planet passes in front of that star, the brightness will slightly drop. And remember, we're not actually seeing that dark dot moving in front of the star. All we have is that brightness, so the star that we see here on the right, that dims a tiny little bit. So we need to monitor many stars over time in order to detect planets this way. Then the second method that we can use is measuring the velocity of the star. And the reason that we can measure velocities is because of the so-called Doppler effect. That's demonstrated in this little animation here. So in this case, the Doppler effect is demonstrated by sound. And this is something you're well familiar with. Whenever there's a police car or an ambulance passing by that is giving all the sounds, you will notice that the frequency of that sound will change whether the car is approaching you or moving away from you. So what you essentially get is that the frequency of the sound changes. And since light is a wave as well, just like sound, it will actually, this same effect, called the Doppler effect, will change the color of the light. So how does this work in practice? How can you find planets this way? Well, when a planet is orbiting a star, it will actually pull the star a little bit away from the center. And while it is orbiting, that means the star is wobbling a tiny little bit as well. We cannot measure the planet itself, but we can measure the spectrum of that star, again, as a function of time. And we see that spectrum, the lines in the stellar light, moving slightly back and forth, becoming a little bit more red, becoming a little bit more blue. And again, based on that, we can deduce that a planet must be present. Then a third method, and this is a little bit more intuitive, is called direct imaging or coronagraphy. So in this case, we are essentially blocking the light of the star, the light of the lighthouse, with a coronagraph in our telescope. And then we try to see what kind of spots are there still present around that. And this is a series of images that was taken. You can see this here, the dates in the lower left corner, of one particular system where we haven't detected just one, but actually 4 planets so far. And what we can see is that the planets are indeed orbiting around the star as a function of time. Obviously, this is only possible for planets that are pretty far away from the star, that we're able to mask the star itself and then still see the planets moving. So this is a little bit of a bias here. We can only detect very bright planets, very massive planets that are far away from the star. And the same is actually true for the other 2 methods. We see these signatures, both the transit dip and also the radial velocity signatures, only when the planet is pretty massive. So just like certain things in life, size matters. The most massive planets give the best signatures, are the most easy to detect. And this is something that we just have to be careful with whenever we are interpreting results and statistics on planets. Remember that we're only sensitive to the most massive ones. Okay, so now that we know that there are many planets out there, maybe we can start thinking about visiting them. And this is where we run into trouble, because distances in the universe are very, very large. Let's start to think of the closest star to us, which is the Sun. The Sun is 150 million kilometers away. Okay, that might be doable. Then let's take a look at our solar system. Let's take a look at Pluto. Pluto is already 40 times further away. That's tricky. Then the second closest star, so after the Sun, is already at 25,000 billion miles. That's Proxima Centauri. And I mean, I know that this all just sounds like very big numbers with a lot of zeros. So let's try to express this in a little different unit, in light time. So you may know that light travels at a certain speed. So that means that we can express a distance in the amount of time it takes for the light to travel over that distance. So in this case, the Sun is located at 8 light minutes from Earth. Pluto is about 5.5 light hours. And that second closest star is at 4.2 light years. So really, there is a lot of emptiness in space. It takes a very, very long time to get to another star, and therefore also to other planets. And this is even worse when you start thinking about what have we done so far? You know, how far have humans traveled? Because the furthest we have traveled is the Moon, and the Moon is 1 light second away from Earth. So try to put that in perspective. That 1 light second is what we've traveled. 8 light minutes to the Sun, 5.5 hours to Pluto, more than 4 years to the nearest star. So yeah, distances are large. It would take very, very long to reach other planets. And then you may say, well, okay, maybe we cannot travel there, but surely we can detect their existence. You know, we can send radio signals and look for radio signals from other civilizations. And although this is true, and this is actually being done, there is a bit of an issue there as well. And that has to do with distance in time. Because if you think about it, the Earth is pretty mature. We are 4.5 billion years old. And the universe is about 14 billion years old. So we are relatively, we've been here for quite a while. But only for the last 500 million years, we've had any kinds of life forms. And for the first few 100 million years, that wasn't even very significant life. Only 200 million years ago, we had dinosaurs. And then later on, we got mammals in maybe the last sort of 50 million years. And then we make a whole next step to the development of humans. 5 million years ago, we had the first human-like creatures, which started to walk on their back legs, started to walk more upright, started to develop tools. But only 100,000 years ago, we had the predecessor of the current human, the Neanderthal. Only 6,000 years ago, we started to have some kind of civilization, like a technology-dominated civilization here on Earth. Remember, this is on the timescale of 4.5 billion years on Earth. If we think about technology, it's even worse, because for most of the lifetime of humans, we didn't have very sophisticated technology. Maybe like 500 years ago, we could say, well, we had the printing press, and then a few hundred years later, we got the telescope, telegraph, telephone. But so this is technology that started to emit signals. But that was only like about 200 years ago. Well, man on the moon, that was a big step in technology in 1950. And then only in the last 50 years or less, we started to get all this advanced technology that was transmitting signals all the time. But 50 years on the lifetime of our planet, that's a very, very short amount of time. And to imagine that another civilization somewhere out there in the universe is in the same technology stage or even more advanced technology stage as we are, well, those chances are pretty small. And well, you may say, well, but we have all this technology now, and now we just sit and wait, and other civilizations are going to develop elsewhere, or maybe are already at that stage. But the problem is that civilizations and basically all kinds of life on planets doesn't survive very long, because there are an awful lot of things in nature that are out there to destroy us. I mean, there are solar flares, there are asteroid impacts, just ask the dinosaurs. There are viruses, well, I guess I don't even have to mention that right now. And then, unfortunately, at least humans are also pretty good at killing ourselves. So the chance that a civilization is around long enough, and us being around long enough, that our technologies will find each other and communicate with each other, are very, very small. So, no aliens. Why study planet formation then? Well, here I like to go to Calvin and Hobbes. If people sat outside and looked at the stars each night, I bet they would live a whole lot differently. I really love this quote, because this is essentially what it is. Imagine sitting outside and thinking about, where do we come from? How small are we in the universe? How did we get here? How did the Earth get here? These are very fundamental questions, both for humans, but for the origin of humans, but also just for the origin of the Earth. So for me, this is my biggest motivation. I just want to understand how we got here and how Earth got here. How did this form? How did this work? And a kind of related motivation here is, which I always find very interesting, is if you think about planet formation and how we thought about planets and life for a very long time in science. Until 30 years ago, the only planets we knew were the planets in our solar system. So we had those rocky planets close to the sun, Mercury, Venus, Earth, and Mars. And we had the gas giants, Jupiter, Saturn, Uranus, and Neptune, further out. So if we put all these planets in a diagram and try to say, well, these are common properties of planets, this is essentially how that looks like. So we have massive planets at large radii, and which are all gas-like planets, and rocky planets close to their host star. But then we started to discover all these other exoplanets, all these other planets out there, more than 4,000, and they look totally different. Not every star has a solar system like we know it. In fact, planets like we have in our solar system appear to be pretty rare. So we have no names for all these different types of planets that we've seen. So they're wide orbit giants, so very massive planets at very large orbits. There are hot Jupiters, so very, very massive planets, but very, very close to their host star. Then there are planets that have masses kind of in between Earth and Neptune, both super Earths and mini Neptunes. Those type of planets don't even exist in our solar system. Not even in terms of mass. And then there are also planets that are called lava worlds. So these are rocky planets that are super close to their host star. That they get so hot that all of their rocky material is essentially lava. Is melted. And then so we have all these different types of planets out there. And then we're trying to think of planet formation. We actually need to take that into account, because all planet formation models were entirely based on how can we explain the solar system. And if we look at another star that has only just formed and is still forming planets, we used to think, okay, how can we form a solar system there? But now we suddenly have to think of all these other types of planets that are also forming. And that means that that we have a lot more possibilities to possible outcomes for a solar system. And ideally, what you would like is a planet formation theory that can explain it all, and that can actually also recreate this diversity in planets that we're seeing. And well, one thing I do want to point out here in term going back to the aliens is that the fact that we find all these different types of planets is actually not a good thing for our idea of finding life on other planets, because most of these other types of planets are not the most happy alien places. So all these planets that are really close to their host star, they're too hot for life to develop. And if they're super close, if they're essentially just consist of lava and raining down lava rocks, well, that's definitely not a place you want to live. Then there are also all these planets that are too far away from their host star, so they're way too cold for life to develop. There are planets that have a huge gaseous atmosphere, so essentially a lot of pressure in the atmosphere that will just splat whatever life forms or arrives on that planet. So it's also not the most pleasant place to live. So we can say, yeah, planets are everywhere, but a whole lot of planets are not that suitable for life. So maybe we were lucky in the way that we got here. But overall, by now we can definitely say that planets are ubiquitous, and probably Earth-like planets as well. We just need to find them. And when we think of planet formation, we want to find this unified theory that can explain the formation of all of them. So how do planets form? And I have a little video here, and it's showing it's actually a very what we think is a very simple process. So we know that there is dust all over the universe, in particular in these large clouds, molecular clouds. Dust particles are moving around and sometimes collide with each other and stick together. And this is a process that can repeat itself again and again and again. And in that way, you can grow larger and larger dust grains and pebbles and planetesimals. So what you're essentially doing when you talk about planet formation is try to find a way that, and try to find the conditions that these grains continue to grow to larger and larger sizes under the influence of a whole bunch of physical laws. And well, we have to remember, we have a lot of steps to go here. We have to go from tiny micrometer-sized dust grains to a factor of 1,000 larger to what we call pebbles, another factor of 1,000 to rocks, another factor of 1,000 to planetesimals, kind of like the things that we see in the solar system in the Kuiper belt. And then another factor of 1,000 before we are at the size of the Earth. And then maybe even a step further, accreting a rocky core like the Earth that accretes gas can eventually become something like a Jupiter, a gas giant. So this is how we think that planets generally form, a sequence of all of these little steps. And then with the diversity of systems that we have, environments that we have out there, we're trying to figure out how we can convert that range of environments, that range of conditions, into this very large diversity of planets. So, um, I was mentioning that this planet formation process just happens spontaneously in dusty environments, but it's actually a little bit more specific than that. We think that planets are forming in so-called circumstellar disks. So these are, you can imagine them like pancakes with a tiny hole in the middle where the star is. These pancakes are made of gas and dust, which originates from a larger cloud. And when that cloud collapses, when that cloud collapses, a star is formed in the very center. And because the material is rotating, an accretion disk is formed around that star. So, and then in that disk, the planets are being formed, and that's how they end up in orbits around the final star. So this planet formation process that I mentioned, this coagulation, this sequence of growth events, we can put that in a computer simulation. We can estimate that it probably takes several million years to form planets this way. And that's an awful lot of time. And I know that you guys in Toronto are used to long-term construction projects, like the Crosstown LRT project. But it's still not the same as a planet formation construction of literally millions of years. So I guess you're lucky there. So we cannot actually see planet formation happen, even if we were able to zoom in all the way to these dust grains. But what we can do is try to figure out the conditions in these large clouds in which stars and planets are forming, measure the densities, the temperatures, the pressure, the radiation fields, the chemistry, etc., etc. All of these conditions can help us to calibrate our computer simulations that speed up the process of computing planet formation itself. Also, we can look for these circumstellar disks and try to see if we can find signatures that planets are already forming. So just to remind you, this process of a combined star and planet formation, as I mentioned, we start with this large cloud, which collapses to a protostar with an accretion disk, and eventually this accretion disk turns into a planetary system. And maybe just to make the circle complete, at the end of the lifetime of a star, it will implode or explode, depending on its mass. Thereby, it will sweep away all the material that is around it, including us, including any planets that are nearby. And then all that material basically returns to the interstellar medium. It forms diffuse clouds, and then the whole cycle starts again. So it's interesting to remember that, with the lifetime of the Earth and of our solar system, we are actually already made out of remnants of previous generation stars and planets. So what we would like to do is study these disks, because we know that planets are forming in these disks, and we want to understand the conditions there. The issue now, studying circumstellar disks, is that they're not very small. Like a typical disk is like 400 AU, and AU is the distance between the star and the Earth, so 150 million kilometers. And that's already like 5 to 10 times the size of the solar system. The problem with these disks is that they're really, really far away, because, well, our sun is already pretty mature, so we and the stars close to us, we have already formed a long time ago. So we have to go to younger regions in the Milky Way where stars and planets are still forming. And the closest regions where this is happening are already hundreds of light years away. And so in order to explain why this is a problem, I'm gonna ask the help here of Peter. So Peter is on Tinder, and he's holding a fish, because that is what guys in Canada do on Tinder. They think that's what we want. But Peter is gonna help me to demonstrate to you how small. You lost my sound? Still? Okay. So to Toronto to the CN Tower, and I'm going to tell Peter to go to the highest mountain in the neighborhood, and that is the well, I'm sorry to say, that is the Blue Mountains. Ontario is very flat, or at least southern Ontario. And I'm going to tell Peter, hold up your fish. I'm going to stand on the CN Tower and I want to see your fish. That fish is the size of a protoplanetary disk at 300 light years. If I try to look at it from the CN Tower, it is that tiny. And well, you may say, well, what's the problem? Because you're not looking with your eyes. You have telescopes, right? And telescopes can look really, really, really deep into the universe. Well, that is true, but telescopes still have a technical limitation, in the sense that the smallest detail that you can see with a telescope, it's called the resolution, is set by the wavelength, so the color where you're looking, divided by the diameter of your telescope. And well, the region, the wavelengths where these circumstellar disks are mostly emitting is called microwave or radio wave emission. And just as a reminder, radio waves are simply a way to indicate the wavelength regime. They're not necessarily signals that you have to listen to with a headphone, like Jodie Foster is doing here next to the VLA, and I try to replicate. Radio waves is simply a wavelength regime. It's somewhere between infrared and, well, what we know as radio waves here on Earth, what you're listening to in the car. So it's kind of millimeter, centimeter wavelengths. That's where these disks are emitting. So if we combine that now with, say, a 30-meter telescope, which is this one over here, the IRAM 30 meter, and we try to use this telescope now to look at Peter with the fish, we're not going to see anything. We're just going to see a blob. In fact, the blob is going to be about 3 times the size of Peter. So we're definitely not going to be able to see the fish or the details in the fish. And remember, that's what we wanted to do. We want to zoom into these disks and try to understand, like, how do they actually look like? Can we see any signs of planets forming there? And this is where a new technology has come in, and which has been very, very revolutionary. This is called the Atacama Large Millimeter Submillimeter Array, or ALMA, which is an array of many, many telescopes that are all working together to get very detailed images of objects in the universe. So ALMA is located in the northern part of Chile, in the Atacama Desert. You can see it in the picture on the upper right. The array is located on a plateau at 5,000 meter elevation. It's surrounded by mountains that are even slightly higher. But you can definitely see this is a very, very isolated area, very dry, which is perfect for these kind of observations. On the lower right, you can see an example of one of the telescopes of ALMA, which is by itself already pretty huge compared to the humans standing next to it. And all of these telescopes were transported all the way up to this plateau and put together in that array to use as an observatory. And the total array actually consists of 66 of these telescopes. And ALMA itself is funded and operated by 4 major organizations: the NRAO here in North America, ESO in Europe, NAOJ in Eastern Asia, and the ALMA Regional Center in Chile itself. And all astronomers living in these regions are able to use the ALMA observatory. So ALMA makes use of a technique that is called interferometry, where you're making use of the concept that light, when it arrives on Earth from a distant source, that light will reach telescope 2 slightly earlier than telescope 1. And because of that time delay, you can combine the light afterwards and then say something about the structure in your source. So to make things simple, because there's a whole lot of math involved, the resolution that you can achieve with an interferometer is the same as the wavelength divided by the baseline length, where the baseline is the distance between the two telescopes. So now you no longer need to build a very, very large telescope. Like we had the 30-meter telescope before, but now you can actually just use two telescopes that are located at a distance of 1 kilometer and simulate a resolution of a 1 kilometer size telescope. And that means that we can now ask Peter to bring Nemo and Dory up to the Blue Mountains. And we're going to look with our ALMA eyes from the CN Tower to the Blue Mountains. And we can recognize Nemo and Dory. We can see all the little details on their fins, on their eyes, etc., etc. That is the kind of power that we have, the kind of resolution that we have with this enormously powerful array of telescopes. So what are the kind of things that we can observe? Well, there, as you may remember from these circumstellar disks, they essentially have two components. There are dust grains and there is gas. And both of these can be studied with ALMA. Dust is probably the easiest to explain. So what dust particles do is absorbing visible light. So we're kind of used to thinking of dust as something that blocks the light from the stars behind it. And the very famous example of that is the Horsehead Nebula, where you can see this is like a dark silhouette against a bright background. However, if you would look at that same Horsehead Nebula in radio wavelengths, in microwave wavelengths, it actually becomes very bright. And that is because dust particles act like a so-called black body. So dust particles are heated up and then re-emit radiation at longer wavelengths depending on their temperature. So something like the sun is also a black body. It emits very strongly invisible light. But if we think of dust particles that are irradiated by a star, they may reach like 100 Kelvin or 50 Kelvin. So about minus 200 degrees Celsius. They will re-emit that light continuously because they're heated up by something, by the stellar radiation, and because of their temperature, emit at longer wavelengths. So this is what we call dust emission. And well, since these stars are surrounded by dust, we can very easily see the dust distributions in these protoplanetary disks through this dust emission. Well, then gas, and this is if you get confused here, don't worry. I will get back to you in a few slides, but I will try to explain it. So when gas, we really think of molecules, right? And molecules in space are pretty simple because we don't have that many elements in space. In fact, a periodical table of astronomy looks like this. Like most of the elements in the universe are hydrogen and then helium, and then tiny little bits of carbon, nitrogen, oxygen, silicium, etc. So molecules in space and also in circumstellar disks are typically like, well, H2 is very common, so molecular hydrogen. But then the second most abundant molecule, CO, is already 10,000 times less common compared to molecular hydrogen. Then we have things like CO2, water, CN, OH, etc. So you can see they are all pretty simple. But it doesn't matter. We can detect their signatures, and they're actually highly relevant in trying to understand the gas structure in these disks. And so the way that we can measure molecules is not through continuum, not through dust emission, but by very specific spectral signatures. The reason for that is that a box of gas molecules will move around because it has a temperature. They will collide, exchange energy, excite each other, and then all the excited molecules lose photons when they drop back to their ground state. And these photons are very specific for each molecule. So it means that if you detect a spectral line from one of these transitions, you can immediately identify which molecule it originates from. And most likely you can determine other properties as well, such as density and temperatures. So molecules and molecular line emission is very powerful in deriving properties about the gas. And a typical spectrum of gaseous objects in the universe contain lots and lots of these molecular lines. So there are many fingerprints all next to each other. And we can use all of them to derive more about the composition of our disk or cloud. And a very important aspect here as well is that we can use molecules to derive information about the dynamics in our system, the movements in our system, because these circumstellar disks rotate around the star. And that means that one side of the disk will move away from us and the other side will move towards us. And because of, if you remember that, the Doppler effect, that means that the line emission coming from one side of the disk will be slightly red-shifted, and on the other side of the disk will be slightly blue-shifted. So by measuring the molecular line emission in multiple places of the disk, you can constrain that rotation pattern. And because of that, this is an actual ALMA observation, we can measure this velocity pattern, which kind of looks like a butterfly. So here we're scanning through all the different velocities in the disk and recognize that the highest blue shifted emission is on one side, and then we go to the lower right where the most red shifted emission is all the way on the other side. This is a very beautiful example of rotation in a disk. So I just want to highlight some of the big discoveries that ALMA has made over the last decade. I think one of the biggest results of ALMA is this the picture that we see, the type of pictures that we see here, which is that many of these circumstellar disks, these are dust observations, show rings and gaps. In fact, almost any disk that we've looked at high resolution has gaps in their dust distribution. And we think that all of these gaps are carved by planets. So planets must already exist here and are cleaning their orbits as they go along. Then there are even more extreme objects. So these are the disks that have very large cavities, very large gaps, which must be carved by very massive planets. So just to put these things to scale, these disks are like 2-3 times the size of the solar system. And whatever planet is carving these gaps is located, well, at the orbit of Neptune at least. And it must be very, very massive in order to clear everything inside that dust ring and all the way out to, well, basically Pluto's orbit or beyond. So the existence of these systems is already very, very spectacular. We even see that some of these disks these dust disks are asymmetric. And that was a very big discovery. We think that these asymmetries are caused by so-called vortices in disks. And a vortex is something that you may actually be familiar with. If you're pouring milk in coffee, you see all this like spiraling movements, all these wavy movements in your coffee. And so this is the result of an instability that happens in fluid dynamics that creates these kind of asymmetric, swirly movements that results in these asymmetries that we see in some of the disks. So this was a very interesting discovery that such a response, basically such a physical phenomenon from fluid dynamics can actually be observed on such large scales as well. We also discovered that a lot of these disks, so they had these dust rings, but the gas was actually behaving somewhat differently. So there's a separation between where the gas is located and where the dust is located. And one of the ways that we can explain that is that the gas is actually helping to concentrate the dust in certain places in the disk, and thereby enhancing the dust growth and maybe even enabling the planet formation process. We've also seen several examples now of disks that have large-scale spiral arms, just like we see in famous galaxy images. And for spiral arms, we actually don't really know what's going on. Is this some kind of crazy dynamics that happening in a disk? Is it a gravitational instability? Is it a gravitational effect? This is still quite a big mystery. Then I mentioned briefly that we can measure the velocity patterns in disks. And here on the left, we see the velocity map of a regular rotation disk. So what we would expect if the disk is just rotating normally around the star with all the red emission on one side and all the blue emission on the other side in this, again, this butterfly pattern. But there's several disks now that have a totally different velocity pattern. They look like a very big warp of emission close to the star. So which implies that gas is actually falling inwards in a swirly motion towards the star. And also here, we don't know exactly how this happens, but it's not just one disk. We've seen this several times. So it must also be something that we must be able to explain with general physics. And then another a very interesting aspect is what we call astrochemistry. So this is the discovery of complex molecules in space, and trying to explain how can we explain the chemistry in these environments. Remember, these are still very low density, low temperature environments, and still somehow molecules are being formed and becoming more and more complex. And we see all these chemical complexity, even in circumstellar disks. And the reason that this is so relevant is that all life that we know, all DNA, has at some point started as this complex organic chemistry. It must have started with very simple molecules that were forming the building blocks for prebiotic molecules that eventually became DNA, and that were then somehow delivered to Earth as well and created life here. So astrochemistry is highly relevant for any understanding of, again, aliens. So one very important thing that we have to keep in mind here is that we have big biases in our observations. And this is true both for the exoplanets and also for our disks. And these biases are actually opposite, and that makes it even more difficult to try to understand how do we convert disks to exoplanetary systems. So exoplanets are most easily detected when the planets are massive and when the planets are located very close to their host star. Because that's when you have the biggest effect in terms of the transit and also for this radial velocity, this wobbling pattern of the star. However, for disks, even though we have now the power of ALMA and we can resolve these disks to incredible detail, we are actually still only sensitive to the brightest disks in order to resolve all this structure. And a lot of the images that we've taken so far are very massive disks, very large disks, where the dust rings are located at, again, several times the orbit of Neptune. So when we're comparing disk and exoplanets, it's very important to keep that in mind, that you're actually looking at different scales. And it's not so clear that you can just down convert that you can rescale these disk systems down to the size of exoplanet orbits or the solar system. And essentially, at this point, we cannot answer the question of what is happening in the inner part of the disk where Earth and so many exoplanets have originated. We simply don't have that information right now. And we have to wait for the next generation of telescopes in order to answer that question. So this brings me to the end of my talk. And I would like to end with another quote from Calvin and Hobbes. I hope I have convinced you that planet formation is a very vibrant, very exciting field. And it really goes back to this fundamental question of how significant are we? Are we just one tiny little planet in the universe where life happened to develop? Are there many other planets with life out there? Or are we just a tiny little dust speck? And the answer is we don't know. We still don't know at this point how unique we really are, but I'm very eager to find out. Thank you for your time.
Thank you very much, Dr. van der Marel. It is indeed quite the fun mystery, as you've, I think, illustrated tonight. Your talk has shown some light, or perhaps even in this case, removed some starlight that was interfering with our planet detections. It sounds like there's a lot of wonderful capacity for exploration and discovery when discovering and studying these other planets. And with all of the planet sizes and kinds and types and orbits that you mentioned, it seems like we could reproduce a lot of our favorite sci-fi systems if we looked long enough, in fact. So very, very fun. And it looks like we've got a lot of questions coming your way. So we'll go ahead and pass over to Blake now for some questions for our speaker. Blake?
Hello. Nienke, my very first question for you, are you telling me that the Crosstown LRT is going to take millions of years to complete?
I'm afraid I don't have the power to comment on that. Let's say I hope not.
Okay, real question here. Ralph asked, are planets detected by coronagraphy, did I say that right? Limited to, are they limited to gas giants?
At the moment, yes, because the most massive planets are always gaseous in nature. And the bright with coronagraphy, we are essentially only able to detect the brightest planets, so the most massive planets. In the future, we may be able to reach down. We may be able to reach down to the super Earth level, but then we're talking about the 30-meter class telescopes that are still to be built in the next decade.
And maybe you've kind of already touched upon this, and this is sort of all intertwined. I was wondering about the planet mass graph that you showed, and it does have a bias, as you say, in that we're kind of limited by our technologies right now at seeing the really small planets. So I was thinking at first the graph is skewed, but that's not a fair statement. It's that there's data missing. We don't know yet about the small planets, right?
Correct. Correct.
Like the Mercury size and the Mars size planets and so on. So will these new instruments that are being built and coming online, will they help in that respect?
Yes, so a lot of the current instruments and telescopes that are in development are meant to fill up the plane in that exoplanet diagram. That being said, it is already possible with the numbers that we have right now to make estimates of how common certain planets are. So regardless of our detection bias, we can still estimate that, for example, super Earths are much more common than hot Jupiters. So hot Jupiters are the easiest to detect, but if you can still make a statistical assessment. Well, if I study so many stars and I find so many hot Jupiters, that tells me that only a few % of the stars likely have those hot Jupiters. Well, on the other hand, for super Earths, we know that they are pretty common, like 20 or 30% of the stars likely have super Earths. And our solar system just happens to be not one of them. So this is, we can already start to make some of those assessments, but next generation telescopes will certainly help to fill up that gap even more, especially for Earth-like planets.
Okay. Speaking of next generation satellites, are you excited at the prospect of what the James Webb will be able to offer or do? It's going to be working primarily in infrared, is that correct?
Yes, no, absolutely. I'm very excited about the James Webb telescope. It will be working in infrared, but circumstellar disks, or let's say the inner part of circumstellar disks, which are very hot, they will also emit in that regime. And we're expecting to get a lot of exciting results there as well on disks. Maybe not so much in terms of structure, so in terms of gaps and rings, because you need even higher resolution for that. But certainly in terms of composition and detecting planets, again through coronagraphy that are still embedded in disks. And another telescope that I'm very excited about is the European ELT, Extremely Large Telescope, that is currently being built in Chile. It's expected to see first light in 2026. So this is a telescope that is 38 meters in diameter, which will work in optical and also near infrared. And that one will be able to make images on similar resolution as ALMA, but then in the infrared. And again, that will help a lot in trying to see, trying to detect planets in disks, and also trace the hot gas and dust close to the host star. So yeah, there's a lot of stuff going on. In terms of radio, there is unfortunately no approved mission yet, but there are plans to expand the current VLA, the Very Large Array in New Mexico, to the next generation Very Large Array, which will extend to over basically all of the southern half of US and Mexico. And that means that we will get even higher resolution than the ALMA telescope in these radio wavelengths. And that means that we will be able to zoom in to the very inner part of disks where planets like Earth are formed. So hopefully that observatory will get approved and built as well in the next 1 or 2 decades.
That'll be pretty exciting. I was actually wondering if there were planned improvements for ALMA that you know of, and would they also help in your research?
Yeah, absolutely. So ALMA itself it's actually meant to be a continuously improving telescope, and that goes for most observatories, by the way. So ALMA is meant to operate and it has guaranteed funding for about 30 years, and it started less than 10 years ago in 2012. So we still have 20 years to go, and at the moment there are already a lot of development plans to install additional receivers so that we can observe at even longer wavelengths with ALMA. Also upgraded receivers that are even more sensitive, or that can cover more spectral lines in a single setting. A lot of this is also technology development that still needs to happen. So we're kind of anticipating that certain things will be ready within the next 5 years or so to be installed on ALMA and be taken in use. So yes, also with ALMA there will be upgrades. We're talking about expanding the array as well, but that is likely a more long-term investment, because that, adding more telescopes is basically a different price range.
The question that was asked before about the James Webb was from Lou on our YouTube chat, and he also asked if an array in space would be technically possible, if it would be useful. We all know that, space telescopes can be very expensive and they have to be perfect, but would a long baseline interferometer in outer space be a good tool?
That's a really good question, and not totally unfeasible, being that it has been discussed. As you mentioned, there are definitely a lot of issues with putting anything in space. First of all, how much money is involved, how easy it is to repair things if something breaks down. But say that you have that amount of money, and also possibilities to go for repair missions. I think one of the biggest issues with putting an interferometer in space is stability, because when you're combining the light from two telescopes in an array, you need to know the distance between your two telescopes down to very, very high accuracy, down to a fraction of the wavelength that you are observing. So that means that if your two telescopes are floating in space, you need to know where they're floating with respect to each other down to that kind of accuracy. And I believe that is the biggest technological challenge if you would want to do something like that, other than, of course, the cost.
Claudio asked, can citizen scientists, amateur astronomers, contribute to exoplanet detection and research using equipment that's available to the amateur CMOS cameras and amateur telescopes?
Yes. So I have to admit that I'm not. I don't remember the name of it, but I believe there is a website where for citizen science of exoplanets, where everyone can analyze data from any of the survey telescopes. So there are lots of telescopes all over the Earth right now that are constantly scanning stars in order to measure possible transit. So in order to measure transit, you just need to measure the brightness again and again and again for a very large amount of time. And a lot of the data is just being made publicly available and is available for analysis for anyone. I think that smaller scale, small scale, backyard telescopes are probably not sensitive enough to detect a planet, even a hot Jupiter that is orbiting a star. But several of the professional telescopes, they do offer their data for public analysis. That being said, even the ALMA telescope has an archive of all the data that has been taken so far. And you don't need to be working at a university or be associated with an astronomy department to download that. When the data is taken, it will be given to the principal investigator, the person who has requested that data set. But they only have access to it for 1 year. After that, it becomes public for the entire community. And that means that everyone here in the audience, if you want, you can download ALMA data and start playing with it. But I have to warn you that the reduction of that data is somewhat challenging, and I don't want to put anyone off saying that no, you cannot do it. But I recommend taking some time in really learning the software at that stage. It's not fully it's not a trivial exercise to reduce ALMA data, but it is possible. The data is there.
Right. Thank you for that information. While you were talking about that, I surfed into Zooniverse, and
right.
I actually found the Disk Detective project. And I actually remember signing up for that, but I haven't done any sort of analysis for that. But that's one example where using shared scientific research from telescopes and facilities that citizen science can help in the analysis, where AI currently can't detect some of the patterns and things like that. We need a human brain and eyes looking at it.
Yeah.
And in fact, Lou just asked a question about that. Can artificial intelligence modeling be used in this research? Are you using that? Are you using AI technology now?
Personally, I am not, but yes, several astronomers start to use machine learning, which is a part of artificial intelligence, now in their analysis techniques, or at least in their modeling techniques. One example of that is actually a student here at UVic. So his research is about developing a machine learning method to run hydrodynamic simulations. So hydrodynamic simulations are of protoplanetary disks are the disks that are calculating how does the disk evolve over time. So while material in the disk is accreting onto the star, the disk planets maybe carving gaps in the disk. The radiation from the star is blowing away material. Lots of processes are happening in these disks as a function of time, and in order to understand that process, you basically need a computer simulation that computes all the fluid dynamics and radiation transport in all the different locations in the disk to see what the final result is. Like how the disk looks like over time. This is a very computationally expensive model, and this student is trying to develop ways of machine learning so that you don't have to run the entire model constantly computing all of these hydro differential equations all the time, but to use machine learning to predict how you go from one step to the other. So yes, this is something that is being developed both here in Victoria and also in many other places in the world in astronomy. I'm afraid that maybe I'm already too old-fashioned, that I haven't actually started with that yet, but I'm certainly interested in getting into it in the coming years.
Hydrodynamics makes me think of a pebble dropped in a still pond or lake and the ripples going out, which curiously looks like your discs from ALMA. So maybe there's a lot more to that. So thank you very much for answering those questions. That's all I have.
Okay.
Wonderful. Well, thank you very much. It's really been great to, as I say, see some of these wonderful answers come in. I'll just have to put in a little plug for my favorite citizen science exoplanets are the NASA Backyard Explorer citizen science. So I actually that's the one I signed up for and then didn't get any further with. So just to go with what Blake was saying before. Thank you once again to Dr. Van der Marel. It has been absolutely wonderful, and I'm sure we could all stay here talking about other planets and aliens and systems for quite a while, but we do have to wrap up. Everyone will go home with thoughts of these incredible, extra solar systems, I suppose. And it has been absolutely great to hear this, all about these different systems from you tonight. And of course, exoplanets are always on our brain a little bit. So I'm just going to go ahead and say, thanks once again to our wonderful speaker, and thank you to our audience for the great questions tonight. And I'm going to hand over to our fabulous president, Tom Luton. Take it away and finish off the evening.
Thank you very much, Elena. Well, good evening, everybody, and I hope you're all doing well. It's been 1 year since we were all together at the Science Center, and it's been a long year, but the light's at the end of the tunnel. So we have that out of the way. Let's get some announcements going. So this is one of two types of meetings we have here online. We have our speaker nights, and we also have our recreational astronomy nights, in which a member of the center will talk about what they're doing or what they're working on. Both types of these meetings are here on YouTube. If you happen to show up for the live broadcast, please say hi in the chat, enter a few questions for the presenters. If you're a new member, please introduce yourself. And if you're coming to us from far, far away from Toronto, please let us know where you're from. So our next recreational astronomy night is on the 7th of April. Blake Nancarroll will be discussing the sky this month. Francois Van Heerden will be discussing the Astro Video Learning Curve, fine-tuning settings to get results. and Ron McNaughton, Microbial Maths on Earth and Mars. As I said, right here on YouTube. If you'd like to present, please contact Paul Markov. Now, our next speaker is a little different. Next month, on the 21st of April, Tim Russ, who you may remember as Lieutenant Commander Tuvok from Star Trek Voyager, will be here online discussing a cosmic trek. You may not be aware, but Tim Russ is an amateur astronomer. We'll be hosting a talk and a Q&A at the end. We'd love to have you join us. So please pencil that meeting in. Coming up at the David Dunlop Observatory on the 27th of March at 8:30 p.m., we have Astronomy Night at the DDO. Up in the sky, the fee varies by age, but you can register online. The links are found at rascto.ca. On the 28th of March, we have DDO Ask an Astronomer with Chris Vaughn. There's a $12.50 fee where you can register again online, links at our website. Now, because of the COVID outbreak, all of our world-famous education and public outreach activities are been pushed out of the real world and onto the online world. Virtual star parties and EPO talks have happened and will continue to happen with Ontario Science Centre, Millennium Square, the David Dunlop Observatory, as I've just mentioned, places like St. Clair O'Connor Community, the Dunlap Institute, with Brownies, Cubs, Scouts schools, as well as New Observers to Visual Astronomy, our NOVA course. For more details, keep an eye on our website and also contact public education at rascto.ca. Because of the outbreaks, our observing sessions are suspended until further notice at Bayview Village Park, at the Long Sault Conservation Area, and at the Ontario Science Centre. As well, the Carr Astronomical Observatory is still closed until further notice. We do have maintenance ongoing on the site, but that's all that's happening. But regardless, we are a volunteer organization, and we are always in need of volunteers. So if you're a RAS Toronto Centre member, and if you're interested in helping, and you've got some free time on your hands, please contact the volunteer coordination team at volunteer@rascto.ca. We've got some job postings that we're currently trying to fill. We are looking for a new head of the Light Pollution Abatement Committee. We're looking for a National Council representative. We're looking for some members to form a marketing committee and to chair that committee. Our AV committee, who have been working so hard over the last year to keep us online, are also looking for additional help. Contact volunteer at rascto.ca for more. Our Stellarium training sessions are continuing. So our level 2 course for March 22nd is unfortunately full, as is the level 1 course for April 10th. However, we still have space in the April 26th course for level 1. Just be advised, this course has been geared towards folks on the East Coast, so it's actually operating under Atlantic time as opposed to Eastern time. More courses are will be offered and planned as well. Level 3 and Stellarium for Educators was planned as well. Full details at rascto.ca/content/Stellarium training series. We regret to announce that we're currently experiencing technical difficulties on our forum. Email delivery of posts is currently disrupted. We're asking folks to please use the forum directly via their web browser in the meantime, and we're asking for members' patience while we try and fix the problem. And this is the point where I get to plug RASC membership. Please join us. We have a lot of fun looking up at the sky. You can renew or join online at secure.rasc.ca. If you are a member and you are facing some financial difficulties as a result of the COVID outbreak, the RASC does have an emergency fund. It's confidential. Give Adela at the national office a shout at mempub@rasc.ca. And with that, I'd like to wish you all a very good evening. I'd like to thank you for joining us. Please follow us on all of the forms of social media. Please like and subscribe and hit the notification bell for more YouTube videos. Be safe and keep looking up. Good night, everybody.